Now let's go to section 5 and begin discussing non-homogeneous case. Here's the general form of the equation. The left-hand side is the same as before. The right-hand side, we have f of t instead of constantly 0. This function f of t is often called a non-homogeneous term. Now, please recall the general solution looks like this. YH plus YP, where YH is the general solution of the homogeneous equation, L of y equal to 0. And YP is a particular solution. It's one solution of this original ODE, but it has nothing to do with the initial condition. Therefore, YP is not the solution you're looking for. I hope everybody remembers that. The particular solution is just one solution of the ODE, and it has nothing to do with the initial condition. It's just one solution. It doesn't have anything undetermined. If it has, then changing the undetermined, then you're going to get more than one function. That's not the case. There's nothing undetermined. So if you put it into the initial condition, you just have pass or fail. You don't have any equations to determine those undetermined coefficients. No, it doesn't work with the IC at all. Now, where are all those undetermined coefficients coming from? They're all coming from YH. So add them together, then we have a solution of this, and also it comes with a lot of undetermined coefficients, and you can determine those using the IC. So that's the general solution. Now, we had been working in this kind of form, but we didn't prove it. In lesson 6, we skipped the proof. I guess now is a good time to prove it, so let's prove this. Here we go. The proof itself, is simple, but it contains some non-trivial ideas, a couple of them. Basically, it's two-liner. However, each line has its own idea. The first line, of all places, we begin from y minus yp. Why? I guess it's just an experience. Try various things and you just fail, and fail a lot until you stumble upon this. I cannot explain any better. Basically, that's the same for all proof-based mathematics, not just this course, but pretty much everything in 3000 level or up. When you have to prove something, try a lot, this and that, and fail a lot until you stumble upon something. That's basically it, experience. But once you begin from y minus yp, it's not too bad. Just apply this linear differential operator L, then what do you get? By linear property, you have Ly minus Lp. See? L of y minus yp here is equal to Ly minus L of yp. Both are solutions of this original ODE, so L of y is equal to F. L of yp is also equal to F. So the conclusion, f of t minus f of t, we have 0. Now, is it helpful? We got 0. Is it helpful? Here comes idea number 2. If L of something is equal to 0, then that something is a solution of the homogeneous equation. The solution of homogeneous equation L of y is 0 has the general solution YH. So whenever you have L of something is equal to 0, that something is YH. Consequently, we have y minus yp is YH. So flip this yp over to the other side. Voila, we have what we want. Yt is YH plus Yp. Let's go back here. Of all places, we are beginning from y minus yp. Why? It's just an experience. But then again, once you begin from y minus yp, it's just an easy computation. L of y minus L of yp, they are both solutions of the original equation, so we have f minus f, which is 0. Now, L of something is equal to 0, so that something is YH. So y minus yp is YH, and flipping over this red function to the other side, we get y of t equals to YH plus Yp. That's the proof. Two-liner, but we have two different ideas there, non-trivial ideas. Okay, so much for the proof, and let's come back to this form. We already studied YH quite thoroughly in the previous section. So for the remainder of this section, let's focus upon how to find YP. Once you find that YP, just add it together to YH, then you're going to get the general solution. How to find YP? One idea here is so-called the principle of superposition, but I'm not going to emphasize this very much because I don't really regard it as an important thing. If you have relatively complicated expression like this, and the right-hand side is sum of several different, fundamentally different non-homogeneous terms put together, then you can separate this one whole equation into several simpler equations, and then you can find a particular solution separately, y1, y2, y3, and so on, and then add them all up, or superpose them up, then that's the YP you're looking for. And then, of course, you can find YH. So YH plus YP, you're going to get the general solution. Now, the question is, solving one complicated problem versus solving several relatively simpler problems, which is better? With computer aid, often this is easier than solving 7 different problems. So why would anybody bother? So I'm not going to emphasize principle of superposition that much. Let's just move on. Finding the particular solutions. Okay, before going over to example problems, let's take care of this. The Laplace transform method, and this is something everybody's already familiar with. This is something we have been doing since chapter 2. So let me go over this very quickly. We begin from the original ODE and take the Laplace transform over each side. And the right-hand side is capital F. Previously we had 0 because we had homogeneous equation, but now capital F. Left-hand side, same as before. Break up all those linear combination, apply the input derivative rules, take like terms together, and this always has to be the characteristic polynomial Q of S, and then this always has to be a polynomial of degree at most n minus 1. I'll use R, and so for capital Y, we have this R over Q, highlighted in blue, which is for homogeneous, and then capital F over Q, highlighted in red, that's for the particular solution. So the homogeneous part will give you, well, the same as before, same thing we did in section 4, and then this is new, the Laplace inversion of this capital F over Q part. Let's go to an example problem and do this. Okay, here's a good one. It's a second order ODE, so let's do this quickly. We already know how to do this. First, the homogeneous part. As usual, we take R over Q. Q is a characteristic polynomial, factor it, and decompose by partial fraction. I kind of overdid it here, and this would have been sufficient. Okay, and then the non-homogeneous part. We need capital F over Q. So let's find capital F first. The Laplace transform of the right-hand side. You can always look up page 123 of our textbook, the Laplace table. If you have e to the at, you're going to get 1 over s minus a. So here we go, that's my capital F. So put it into the numerator and then simplify a little bit. And then you can run this decomposition by partial fraction. Yes, it's this one. These two are nothing new because they're going to be ate up by these two. So that's homogeneous parts, so I don't really have to worry too much about those. And then let's just do the red part and take the Laplace transform. Laplace inversion, excuse me. So this red part becomes 2/3 e to the 1/2 power of t. That's my yp. And the previous two gave me the homogeneous part. Okay, the repetition of what we did in chapter 2, or excuse me, yes, repetition of what we did in chapter 2, but also the repetition of what we did in chapter 3 as well, or lesson 6. Okay, Now, we went through the Laplace transform method. All right. Now let's talk about substitution method. In order to find in order to find this yp, let's begin with this f. And based upon what f is, we're going to make an educated guess. Substitute it in and then find out the coefficient. If this right-hand side is an exponential function, we're going to take the same exponential, so c times same exponential. And then take all those derivatives and put everything in here. And then set up the equation, and exponential part will be common, cancel all out, and you're going to get an equation of c. If the right-hand side here is sine or cosine or both, then you're going to get sine and cosine. Put everything here, and sine becomes cosine, cosine becomes sine when you take the derivatives. So both sine and cosine will show up. And then you have sine part and cosine part. We have those two parts, and then consequently you need two equations, two unknowns. Solve them, you're going to get C1 and C2, and so on and so forth. Basically, it's just trial. That's for the simple case, but for some a little bit more serious case, you may have to multiply the t to some power. We're going to discuss those kind of things in actual example problem. So that was substitution method. Let's go back to this problem. We just did Laplace transform method, and that's good. But imagine you don't really want to take this decomposition by partial fraction, and you're going to do everything in paper and pencil method. Maybe this method is easier. Okay, let's go. Here's the homogeneous part. We begin with an educated guess, y equal to e to the st power, and take the derivatives and then put everything in. And once you do that, you have to have the characteristic equation. So this part, actually you can skip, because always you're going to get the characteristic equation. So the zeros of the characteristic polynomial, we have 1/4 and -1. Consequently, we have these. Alright, so much for the homogeneous part. Next, particular part. Right-hand side is e to the 1/2 power of t, so I'm going to make this educated guess. Yp is c times e to the 1/2 power of t. And then calculate the first derivative and second derivative. Plug everything to the original equation. See what happens. Y prime is this, so that goes here. That was y double prime, second derivative. Y prime, first derivative is this, and that goes here. And then original goes there. And then the right-hand side, e to the 1/2 power of t. Do you see exponential is common to everything? So you can cancel all those out. Yeah, divide all those exponentials out. Yes, you can, because exponential is never 0, so you can do that. Then you're going to get an equation of c. You can solve it. You're going to get 2/3. So this is 2/3. Yp is 2/3 1/2 power of t. Homogeneous, particular. So if I add them up, here's my general solution. This method here is the method of substitution. You start from educated guess, take those derivatives, and then put those into the original equation. So what's left here is going to be an equation of the undetermined coefficient c. It's not too bad. In this case, it wasn't bad at all. If you want to do this paper and pencil computation, probably this was better than this decomposition by partial fraction that we did previously. If you use computer algebra system, then of course Laplace transform method is better, because you can decompose by partial fraction using computer algebra system. But if you don't have those kind of technology aid, then this method is superior. By the way, the substitution method is developed in 18th century, if I remember correctly. So there is a strength there. Okay, all right, let's go to the next problem. And this is going to be a heck of a lot more complicated because we have fourth order linear ODE, and thus the characteristic polynomial will be quadratic. Oh, that's a challenge. Okay, this time let's begin with substitution method first. First, the homogeneous part. Okay, alright. You can take e to the st and calculate the derivative and plug those in if you want to, but it's better to skip those because always you're going to end up with the characteristic equation. So set the characteristic polynomial equal to 0, factor it, get all those zeros of the characteristic polynomial, and you're going to get negative 1/2, positive 1/2, and plus or minus I. Consequently, we have these four. Any question? Well, this is homogeneous part, so I trust everybody can do that. Okay, let's go to the particular part. Maybe you'll have to do this, right? Yp is equals to exponential of 1/2 of t. C times of that. But there's a problem. If you do it that way, this term here will eat it up. You see, the homogeneous part already has this term. So this term here, which I just highlighted in bold green, will eat up this. So we have to do something more. How do I do? Multiply by t. So this is the correct educated guess. So we need extra t. Okay, we take c t times e to the 1/2 power of t, and the second derivative turns out like this. Oh my goodness. And the fourth derivative turns out like that. And they are unpleasant computations because we have to use product rule and chain rule. Well, anyway, that's the fourth derivative. It goes over here. That's the second derivative. That goes over here. And then finally, this is the original. So the derivative computation here is already horrendous. Now, let's simplify this. I guess that's not too bad. We have exponential, which is common to everything, so remove everything. And you have just linear part. So the coefficient of t and the constant part, we have those two parts. So basically we have a system of two linear equations, but we have only one character c. Will it work out? Magically it will work out. We have c equals 1/5. It works out. See, this part is always 0, so it doesn't really contribute. Okay, alright. So we got c equals 1/5. So the particular solution is 1/5 t times e to the 1/2 power of t. Added up with the homogeneous solution, we have the general solution like this. It's not a pleasant computation, you see. After making an educated guess, taking the derivative 4 times, oh my goodness, using all those product rule, good luck about that, and then plugging everything in here and set up the system of a linear equation, and then getting c is not a pretty computation, but it works out. At least it's better than decomposition by partial fraction. Laplace transform method is like this, usual, decomposition by partial fraction, and this decomposition by partial fraction, f over q, I mean, this is crazy. I mean, with computer algebra system, it's not too bad, but real paper and pencil computation is crazy. So capital F over q, and getting that, and this is the non-homogeneous part because the others are all covered by homogeneous, so that's the non-homogeneous part. And if you take the Laplace inversion, we get the same thing as before. With technology aid, it's better to do it this way, the previous method that we had been doing from chapter 2. Choose your poison.